Okay, hello physics class. So we're going to continue to build on what we've already learned. So we're going to learn about work, right? We've all heard about work. Kinetic energy, you may have heard that term, potential energy. We're going to work with springs, right? We've worked with gravity. We're going to continue to work with gravity, but we're going to worry about springs, right? Oscillations. So yeah. Chapter 6, Energy and Oscillations. Let's get into it. Right. Yeah, this just builds on everything we've been doing. It takes it to another level. It's good. It's a good chapter. Okay, Chapter 6, Energy and Oscillations. All right, so here we have a pendulum swinging, right? We've all seen that, or you can just do that. This is like, well, looks like it's some sort of necklace. They're just holding a chain and sort of, right? But if you pulled it, you had some energy, then gravity pulls it down, but it doesn't just stop at the bottom. It swings all the way to one side and goes back and forth. So it has energy. And it's oscillating, right? Guess what? Oh, and this is everywhere, right? Your car has a shock absorber, so there's springs in there, but then there's dampers to stop the oscillations, right? So this is a huge field. Okay, so the force does work to move the ball, right? So we know about force, right? We've been studying that. This increases the ball's energy, right? So this person had to grab the ball. They used energy to move the ball here, but now the ball has energy. Because if you release it, and there was something here where the ball could hit it, right? So it has energy. You've given the ball energy. And then we've all used a crowbar, or you've used a screwdriver to prise something, right? So why is it would be difficult to lift this heavy rock, but if you use a long lever, then you can do it easier, right? A simple machine. Well, the secret is that, so you're thinking, how does that happen? Where does that, but the secret is you can only move the rock a little bit here, but although you use a smaller force, you have to move it through a longer distance. So that's how you get a mechanical advantage. So you're able to lift something heavier, but it comes at a cost in that you have to move this side a farther distance, okay? Simple machine. Now this is really good. So notice here, this person, if you were to try to lift this box, it would be very, very heavy. But now you have pulleys. But notice this. The tension in all of these is the same. So you've actually reduced the tension in this rope. Now again, it comes at a cost. You have to pull this much farther. So you have to pull the rope farther. So this crate will only go up a little bit, but you can lift more weight. So it's a mechanical advantage. Let me go back. I just want to go back to this one here. All right, there. Yeah, small tension applied to one end delivers twice as much tension to lift the box. The small tension acting through a large distance move the box a small distance. Okay, so that's what I said. So here, the mechanical advantage is 2. You are able to lift 2 times as much weight. Not bad, right? Not bad. Of course, you have to pull this a farther distance. Okay, so we're going to define work. right? We think of work, well, you think, well, I'm doing work right now. Well, yeah, but not in physics, right? In physics, a lot of terms that we use the term somewhat differently than you would use it in your regular life. So in physics, work is equal to force times distance, okay? So that's what work is in physics. It's force times distance. And so force, the units would be, of course, force is a Newton. We're used to that. Distance is in meters. We've been doing everything in using meters. We're not using centimeters or anything like that too much, right? If you do, you got to convert it. We're keeping everything in Newton meters. And we call that a joule. So you have a new unit to learn, a joule. And 1 joule is equal to 1 Newton meter. Okay? Oh, this is interesting. So the only forces parallel to motion do work. So here this is something, you know, maybe, so you're trying to pull this block, and this is normal, right? You would grab it here, you would pull it, you're trying to drag it along. You're thinking, well, I'm doing 15, I have 50 newtons of force that I'm applying here, so I'm doing, but how much work are you actually doing? Okay, the only part that's doing work is the part that's moving the block. So you've moved it this distance 30 newtons. Although you've applied 50 newtons, we don't count this part. So you're like, what? You're not counting all that force I did? Nope. Nope, we only care about the result. So work, right? So it's sort of a new definition. You have to think it's like a new word, right? So it's like theory. Theory, right? The theory of gravity, theory of evolution. Well, it's not just a theory the way we use the word in our normal day-to-day life. In science, a theory is much more of an important thing. It's a much more established thing, right? Gravity, you know, because there's still things they don't understand about gravity, right? There's gravitational waves, there's gravitons, there's particles, and all that sort of stuff. So there's still a lot to be understood. So that's why it's a theory of gravity. But it works all the time. Same with evolution. Evolution is established, right? We've only been on this planet a limited time. There was lots of animals that were here before us, right? So we've evolved, right? Okay, so here, the only part that's contributing to work is the 30 newtons that's moved this box from this position to this position, okay? Power, right? We've all heard about power. I want power. Well, it's not that kind of power. Power, here we mean like, you know, the power plant that makes electricity for your house and that sort of thing. So power is work divided by time. So this is another, and we're calling it a watt. Well, you've heard of watts, right? You have like a 100-watt light bulb, or, you know, in your fridge, there's usually like a 25 or a 15-watt light bulb in your microwave, in your oven. You'll have those sort of things. And I'm talking about the old-fashioned light bulbs, the ones where there's a filament that gets warm, incandescent, right? I'm not talking about the newer ones now that are LEDs and they don't get warm. We're talking about, like, I'm referencing like a 100-watt light bulb. A 100-watt light bulb, it's easy to have a sense for what a watt is. If you have a 100-watt light bulb, you know how much heat, you know how much light. So you have we as a human can have a sense for what a watt is. If you have 10 100-watt light bulbs, that's 1,000 watts. That's a kilowatt. You've all heard of a kilowatt. Well, it's 1,000, right? You've all heard of a megawatt. Well, a megawatt is 1,000,000, right? You've all heard of a gigawatt. You know, the power plant is making gigawatts. What's 1,000,000,000 watts, okay? You understand watts, henceforth and forever. But it's joules per unit time. So it's the rate of doing work. So you're doing work, but a joule per unit time. And we're going to get into this more. So, okay, a string is used to pull a wooden block across the floor. The string makes an angle. Does the force applied via the string do work on the block? C, only part of the force does work, right? We've already covered that. This is the little test. Okay, if there is a frictional force opposing the motion of the block, does this frictional force do work on the block? The answer is A, yes. Yes, of course it does. Since the frictional force is anti-parallel, oh, that's a funny word, to the distance moved, it does negative work. So if you're pulling this, right? Well, yeah, sure, because we've already done problems like this. If you have a force going this way and there's an opposing force, then it's the net force that you're going to worry about, right? That's going to count into moving the block. Yeah, and the normal force, that would just be the force of the ground or the table that's holding this block up. That does not do work on the block. All right, let's move on. I think we've covered this particular. Oh, we've covered that one. Okay, kinetic energy. You may have heard this term, kinetic energy. So here you have a crate sitting here. The velocity is 0, the kinetic energy is 0. It's just sitting there, it's not doing nothing. But if it's moving, now it has kinetic energy. It has kinetic energy because it could hit the wall and make a hole in the wall, or it's moving, right? It has energy. Or it could hit something else and move that. Well, it takes energy to do that, right? And it's the mass, right? And then it's proportional to the square of the velocity. So the faster you're going, the more kinetic energy you're going to have, and it's squared. So it means that if you're going fast, the kinetic energy builds really quick the faster you're going. Yeah, it's associated with an object's motion. Doing work on an object increases its kinetic energy. So work done is a change in kinetic energy. So work and kinetic energy are related. If you do work, you change the kinetic energy. Guess what? They have the same units. Let me go. Well, yeah, I already said 1/2. We'll go back. Let me just look at that one again quickly. Okay. I hit that too soon. And just so you can see that, kinetic energy is equals 1/2 mv squared, as we stated. Okay, so here you have some guy in a sports car, right? Trying to be cool with a sports car. So negative work is the work done by a force acting in a direction opposite to the object's motion. So a car skidding. So here this person, they're saying he's skidding. So now, right, the tires will have friction with the road. The tires will heat up. That's what happens with the excess energy, right? It goes into thermal energy. We're going to talk about thermal energy later on, some chapters coming up. What force is acting to slow the car? Okay, well, we know that, frictional force, right? So let's talk about potential energy, right? So I'm going to lift up this marker to a higher position. Okay, I've lifted it, right? It now has potential energy. If I drop it, it hits my hand. But if I lifted it really high, well, we know it's going to fall. It accelerates, so it's going to hit my hand with more of a force, right? So the potential energy is increased if I lift it higher and higher. If work is done but no kinetic energy is gained, we say that the potential energy has increased. Okay, so if a force is applied to lift a crate, the gravitational potential energy of the crate is increased. Well, yeah, this makes sense. If you just lift a crate a couple inches and you drop it, well, you know, hopefully you don't break anything on the inside. But if it dropped from the top of a building, well, heck, you could crack the sidewalk, damage, right, a car, right? So it's going to have a lot more energy. But while it's sitting there, before you drop it, it has a lot of potential energy. It's dangerous, right, that crate. So work done is equivalent to the force, right? The mass times the gravity, right? Force is equal to mass times acceleration, but G is the acceleration due to gravity, times the distance, so mgh. The gravitational potential energy equals mgh. H is the height, right? So the gravitational potential energy is force, mg, times height, okay? Okay, work is done on a large crate to tilt the crate so that it is balanced on one edge, rather than sitting squarely on the floor as it was first. Has the potential energy of the crate increased? Yes. Yeah, they did. I mean, it's the center of the crate is a little bit higher, right? So that is the amount of potential energy. If you let this thing go, it's gonna thump down, right? And while it's falling, it's going to have kinetic energy. While it's just sitting there, it has potential energy. As it's moving, it has kinetic energy because it's moving, and then you'll feel that when it thumps on the ground. Yeah, potential energy. You've stored energy. You've stored energy. I grew up in a town called Niagara Falls. In Niagara Falls, we get our electricity from they divert a lot of water from the Niagara River. Instead of going over the falls, it goes under the city, and it goes all the way around to where there's a canyon, right? The Niagara falls into the water goes into a gorge, and then it flows into Lake Ontario. Well, what they do is they divert it. They divert a lot of that water, and instead of it just going down into the gorge, it turns these turbines, and they make electricity. So we get all of our electricity from the potential energy of the water that's higher, and then as the water's flowing down and turning the turbines, it's turning it into kinetic energy. Okay? And then we get electrical energy from that. So yeah, and then you don't have to have, you can get potential energy from a lot of different sources. Here we're going to talk about a spring. Everyone knows if you pull a spring, right, if it's a big, strong spring, you would have to pull it, give it a lot of force. Well, now if you're going to release it, that's going to be kinetic energy. While you're holding it, while you've pulled it back, that's potential energy. It's like, oh no. And if you release it, it's going to have kinetic energy. And then as it's oscillating back and forth, so you pulled it, it's going to have a lot of potential. Then you let it go, it's going to oscillate through. So the potential is being converted to kinetic, and then right at the end here, it stopped. It's all potential energy again, and now it's potential and kinetic, right? And it keeps going back and forth that way. Yeah, so it's an elastic potential energy. And what they'll do with a spring is they'll give it a rating, right? So a big stiff spring, like in a truck, is going to have a different spring constant than one that you have in your the front fork of your bicycle or something like that. Or in a ballpoint pen, there's a little spring. Right, there's a little spring, right, in this pen, right. So it's going to have a different spring constant than something in a truck, right. Okay, and these are very similar to what we've done before, right? With distance. So the forms are similar. I have a separate video where I'm going to go through all of the formulas for this chapter, right? And do a summary there. So that's why I'm not going to be talking to them in too much detail here, because I do all that, where I show all the units for all these potential energy, kinetic energy work. They all have this, it all comes down to the same units, right? I will demonstrate that in another video. But it's good to see this first before you watch the other video. So, okay, this is an excellent diagram. So here you would have a pendulum, right? A pendulum, you have a long string, and then you would have a ball on it. You would pull the ball and release it, and it's going to be going back and forth. So when the ball is just sitting there and not moving, it doesn't have potential energy, it doesn't have kinetic energy, it's just sitting there. But if you grab it and pull it and then stop here, now it has a whole bunch of potential energy, mgh, right? We talked about that. Mass times the acceleration due to gravity times the height. Now you let it go, And then when it gets a little bit lower, now the potential energy has decreased, but the kinetic energy is increasing because it's going faster, faster. When it gets right to the bottom, it doesn't have any more potential energy from mgh, but it has all kinds of kinetic energy from 1/2 mv squared. This is the fastest it's going to move. Then as it continues, it starts getting slower, slower, slower. So the kinetic energy is decreasing, decreasing, but when it gets way up to here, now it's at the highest point for potential energy up here. And so you keep transferring from potential, you know, and then potential energy is getting less, kinetic energy is getting more, right? And it goes back and forth and henceforth, okay? Conservative forces, you may have heard that. Gravity and elastic forces are conservative, right? We just went through that. Friction is not conservative, right? This thing's eventually going to slow down because you have air resistance and friction and air resistance. That's not conservative. That is the enemy of a conservation. It just dissipates. Friction, it converts it into heat. Air, you've moved the air around. It took energy to do that, right? So. Yeah, so it remains constant. As this pendulum's going back and forth, the potential plus the kinetic is always the same. Up here it's all potential. Down here, when it's straight down, it's all kinetic, and in between it's combinations of the two, but it equals the same value. Okay, so here we're back to our simple machine. So a lever is being used to lift a rock, okay? The work done by a person can never be less than the work done by the lever on the rock. So if there are no dissipative forces, they will be equal. So all they're saying is that you know, here you're using as much work, you're doing as much work over here as what's happening here to lift a rock, but the difference is you've made up the difference because you have to move this a farther distance, right? So your force is decreased here, but the distance is increased, and work is equal to force times distance, right? Here it's force times distance, but it's a shorter distance, okay? All right, and the sled, I prefer the pendulum. I think the pendulum one is easier to think about. This is in the book though, if you want to go through this one, but I think the pendulum one works well. So, okay, simple harmonic motion occurs when the energy of a system repeatedly changes from potential energy to kinetic energy and back again, right? We talked about that with the pendulum. Well, with a spring, you can get the same thing. You would pull this, and then when you let go, the spring is going to go, it's going to compress, but now the spring is compressed, and so it's going to push, and it'll just keep going back and forth, back and forth. What happens in real life, this eventually stops because the spring heats up, so you dissipate energy in heat. There's frictional forces because this is dragging on the ground, right? So those things stop it. But if you didn't have any friction, and if the spring was a very elastic spring and it didn't dissipate a lot of heat, this oscillatory motion could go back and forth for a long period of time. Okay, and this is showing we're talking about oscillatory motion here. So this T here stands for the period. So the period is one cycle. So it'd be from peak to peak. It's just a way to measure graphs, and you know, an amplitude is how big when you're plotting, you know, a back and forth motion. So it would have, you know, as a function of time, a pendulum or a spring are going back and forth, and it keeps repeating, right? So the amplitude is how big it is. And then period, how long it takes for one cycle, your time, say that's in seconds, right? So that would be like cycles per second. So, okay. Frequency is the cycles per unit time, right? And that's it, folks. All right.